Okay, so yeah, so that concludes kind of the first part of this lecture. Now we're actually going to look at more of the Laplace transform properties. Okay, so we're going to look at a very interesting property of the Laplace transform. In particular, let's look at a function f of a times t. If we know the Laplace transform f of s, so let's write out this integral. We have 0 to infinity uh, f of a t e to the negative st dt. What we can do in this particular case is we can write an auxiliary variable t prime, which will be equal to t over a, or sorry, not t over a, I apologize, at, so that now we can rewrite our integral as 0 to infinity of f of t prime, and then dt prime dt is equal to a, which means that dt is equal to dt prime over a, so 1 over a, e to the negative s t over a, the t prime over a, and then we can actually rewrite s as, we can define s prime as s over a, and so that now we have 1 over a, the integral from 0 to infinity of f of t prime e to the negative s prime t prime dt prime. So this is just equal to 1 f of s over a. Sorry, oh god. F of s prime a. And so the more important thing is actually that this is just f of s over a over a. So what's interesting here is if I take a function, let's say f of t, and let's say it goes from -1 to 1, then that means that f of a t goes from negative a, sorry, from 1 over a to -1 over a. It's going to be 1. And let's say the Laplace transform of this function looks something like this. Where this is just for argument's sake, let's just say this is negative pi and this is pi. Then the new Laplace function will actually be a times pi, negative a times pi. So what's interesting about this is that if we make things smaller in the, let's say a is greater than 1. So if we squish something in the time domain, in the Laplace domain, it has to get expanded out and vice versa. Now, this actually means that later when you learn, what you will learn is that actually this is a general property of functions, which basically says if your switching speed in a system is faster, the amount of bandwidth or the kind of the range where the non-zero part of your signal is increases. And so what that means is that if you want to increase data rates in most engineering systems, you actually will need more bandwidth, and this is why bandwidth in like common culture is such an important thing. At this point, you can actually see this through this property of the Laplace transform. Of course, you don't know enough of the background material, but by the end of this class, this will make a little more sense. Additionally, when we talk about Heisenberg's uncertainty principle, there's a relationship like this that is attributed to both the speed and the location of a particle, and which basically says that because these two things are related in such a relationship, if you know a lot about the other one, you don't know much about the uh, other things. So if you know the location, you don't know a lot about the speed, and if you know a lot about the speed, you don't know a lot about the location. So all this comes about this property that we just derived in this slide. So here it's done a little more cleanly. Instead of using t prime, I use tau. So then I got this, and then I rewrote it, and then I got my answer. Okay, so let's say we want to find this Laplace transform. To be honest with you, usually I'm going to say go to the table, but for this one, it might be easier to just go to the integral form because you're just going to be integrating. You just have to figure out the limits of your integral. So you basically have from 0 to infinity 3 u of t minus 1, u of 4 minus t, u of t, e to the negative st. So this one is 0, or this one is 0 whenever t minus 1 is less than 0, which means that whenever t is less than 1. Then this one is 0 whenever 4 minus t is less than 0, which means when t is greater than 4. And then this one is 0 whenever t is less than 0. So our lower limit will actually be 1, because that's when this thing turns on. Our upper limit will be 4, because whenever t is greater than 0, the function will be 0. And now we just have to do the integral. So we're going to have the integral from 1 to 4 e to the negative st dt. That's going to be equal to 3 over s negative e to the negative st evaluated at 1 and 4. And so we're going to have 3 e to the negative s minus e to the negative 4s divided by s. And I switched the order so that I can get rid of the negative sign. And that's it. That's our Laplace transform. Okay, so here's the answer to that question. And let's go to the next slide. In the previous half of the lecture, we went over all of these Laplace properties here on the left. And additionally, we went over this one. We still have 3 more properties to go over. So let's just go over those really quickly. So let's say functions multiplied by t. So let's say we're given f of t and f of s, and we want to determine g sub s, where g sub t is actually TEF of t. So to do this, we can actually do the following. We can associate this t with the Laplace transform part, so that we basically move this t and associate it with this. Now this actually becomes negative the derivative with respect to s of that term. And so then we can actually just factor out this derivative with respect to s, because it's not in terms of t. And so what we get is actually that it's just the Laplace transform f of s differentiated. Now notice something really interesting right now, which is that when we multiply a function with t, so t f of t leads to negative s f of s. Assume zero initial conditions for a little while. Sorry, not sf of s, ouch. We just derived this. Okay. But then we also know that f of s, if we assume zero initial conditions, also led to d dt f of t. So essentially, if we multiply by t in the s domain, we're taking a derivative, and if we multiply by s in the time domain, we're taking a derivative. So this is kind of a manifestation of what we call duality, or that if you do something in the time domain, or you do the same thing in the s domain, its effect in the s domain and time domain will be effectively the same. So there's kind of this duality. I multiply by t, I get a derivative in s. I multiply in s, I get a derivative in t. And vice versa. Okay, so that's kind of an interesting. Okay, so I already kind of showed this, so let's move on to the next slide. All right, so given f of s, can we determine something multiplied by t squared? So we already know basically that we know that the Laplace transform of t times t f of t is equal to d ds of the Laplace transform of t f of t negative. That's what we just derived in the previous slide. And then we can apply this property again to get that this is just negative dds, sorry, times negative dds f of s. So we're going to get that this is actually dds squared squared f of s. So see how we can get additional Laplace transform by just using these properties over and over and over again. So yeah, so that's kind of and in general, this would be kind of for any power of t to the n times f of t. Now, why would we want to do this? Well, look, we had u of t got us 1 over s, right? But we additionally wanted to know what tu of t was. Well, that would just be dds of 1 over s negative, which is just 1 over s squared. So we don't even have to do all those integrals we did in the previous slides. We can just get it very quickly. Now, in particular, in differential equations, we know that we're going to get things that look like this a lot, t negative at. That's when we had our critically damped responses. Well, that's just going to be equal to, if we look at our Laplace transform, it's just going to be dds negative 1 over s plus a. Well, that's just going to be equal to 1 over s plus a squared. So see how easily now we can do that Laplace transform without a lot of effort. So that's why these properties are important. Okay, so we did this on the previous slide. So we said that basically to analyze this, we would just say that this is equal to negative dds, sorry, of 1 over s plus a, which is just equal to negative 1 times kind of dds of s plus a to the negative 1. So it's just going to give us negative 1 times negative 1 s plus a squared, because we subtract 1 from negative 1, we get negative 2. So let's say we want to do this one. Well, if we want to do this one, that's just going to give us that this is actually equal to -1 to the nth power dds to the nth power s plus a to the -1. So if we take the nth derivative, it's just going to be -1 times -1, -2, -3. So each time we are taking a derivative, we're going to be decrementing 1 in the power up to -n, because that would be the nth derivative. And then we get times 1 over s plus a to the n plus 1. Now, these negatives, so remember that this is to the nth power, will each cancel one of these negatives so that we actually end up with just a simple n factorial s plus a to the n plus 1. So now you can do basically any power of n, so you can do as many repeated roots as you have in your differential equation. Luckily in this class you at most will have one repeated root, but now you can do it all. Okay, so here's that formula more cleanly. Now let's go ahead and do, okay, now let's look at functions that are shifted by a t0. So what I did here is I multiplied, I basically went back to my integral definition of the Laplace transform. And then so my pen's not working. Okay. So I went back to the integral definition of the Laplace transform, and then I now replaced it by f of t minus t naught. In general, we're going to assume that for time less than 0, f of t is 0. So that if I plug in here t minus t naught is less than 0, then our function is 0. So that means that whenever t is less than t naught, our function is 0. And so we don't have to go from 0 to t naught. Additionally, now we can introduce an auxiliary variable. So we're just going to replace this t minus t naught by a gamma. So we have gamma t minus t naught, and d gamma will be equal to dt. So we're going to be left with this. And then we can factor out this e to the negative st naught, and we're left with the Laplace transform definition. So we will get that g sub s, if we shift in time, we multiply it by a decaying exponential in the Laplace domain. What do you think will happen if I shift in frequency or in the Laplace domain? Based on duality, my guess would be that what's going to happen is that we're going to get e to the negative at f of t. But in the next slides, we're actually going to confirm that indeed this is the case. So remember that duality says that if I do something in the time domain and I get something in the frequency domain, if I do that same thing in the s domain, I should get the same thing in the time domain. But let's confirm it. Okay, so now we're actually looking at functions of this form. And now what I'm going to do is I'm actually going to combine the two exponentials so that I end up with this. And then I'm going to define a new gamma variable. And what I end up with here is actually that in terms of gamma, this is just the Laplace transform in terms of gamma. So we get f of gamma. And so see, the s now became gamma. And now we replace for gamma f of s plus a. And so indeed we get f of s plus a is multiplying by the, so if you shift in the frequency domain, you get multiplication with a exponential. And if you shift in time in the frequency domain, you get multiplication by an exponential. So this is another manifestation of duality. Now, this is another way we could have done the this particular Laplace transform. So we know we in our very first slides we derived this. We could have said by the frequency shift that f of s equals 1 over s for u of t. And so e to the negative at u of t gives me f of s plus a, which is 1 over s plus a. So we could have derived this using the frequency shift also. So these properties are very useful because then you can avoid doing integrals. Okay, so that's it. What else do we have here? Yeah, so like I said, there's this duality principle. So as you can see, the cross terms are the same. Same thing happened when we did differentiation and integration. That's a general property of the Laplace transform. So once you can do it one way, you can infer what's going to happen in the other way. Time integration. Okay, let's go over this one last Laplace transform. So if we know f of s, and let's say g of t is actually the integral of f of tau d tau. So what we can actually do here is effectively multiply and divide by s this equation, or by negative s, so that now this is actually the derivative of e to the negative st. And now we can apply integration by parts, where u is this, so that this is du dt, and then v is whatever's left over. So now we get uv, and then we have to take the derivative of this with respect to tau, or time, which by the fundamental theorem of calculus, that's just f of t. And we still have the negative 1 over s, e to the negative st, which is u. But this is just the Laplace transform of f of s divided by 1 over s. And then we have here our initial condition term, which came from the uv part in the integration by parts. We're rarely going to be using this formula, but it's in the textbook, so I just went over it. Okay, so I think that covers all of the properties of Laplace transforms. Everything you want to know about a Laplace transform is actually summarized in the two tables. Those will be given to you in an exam. And in particular, the kinds of things you need to know is how to use the tables. So in the last 5 minutes of class, I'm going to go over what's actually relevant, which is how to derive new Laplace transforms from existing Laplace transforms. So we're going to actually find what x of s is for this particular function. But to do that, since we have a delay on the unit step function, that kind of hints to us that we want to use this delay property, time shift property. So what we're going to do is we're going to write this in a clunky way as 2e to the negative 4 t minus 2 plus 2 u of t minus 2, and that's just going to give us 2 e to the negative 8, the Laplace transform of e to the negative 4 t minus 2 use of t minus 2. And now we can use this time shift property to say that this is just actually equal to, so we need to take the Laplace transform of this, so Laplace transform of this, and we can factor out all the constants. This is the Laplace transform. Now we can use this time shift property to get rid of the delay by 2, so we're going to have that this is just actually equal to 2e to the negative 8 e to the negative s 2s, sorry, let me just erase this, 2s, the Laplace transform of e to the negative 4t u of t. And then now we can look this one up over here, so that we have 2e to the negative 8 e to the negative 2s divided by s plus 4. So you can use these things to get more complicated Laplace transforms. Okay, so yeah, so that's what we got in the previous slide. Okay, so let's go to the next one. Let's say we wanted to find the Laplace transform of this one. So here we have to play our trick again. So we know that x of so since we have a delay in the unit step function, we also have to find a way to delay our cosine. Hold on, my pen's failing me now. Okay. Okay, there you go. So we have to basically find our cosine. So we have cosine of 12 pi t minus 2 plus 24 pi plus pi u of t minus 2. But remember that since cosine is a periodic function, if you add 25 pi to it, that's just equal to negative cosine of 12 pi t minus 2 use of t minus 2. So now we take the Laplace transform of this thing, and that's just going to give us e to the negative s2s, the Laplace transform of cosine. So Laplace transform of cosine 12 pi t u of t. And that's just going to be equal to e to the negative 2s s over s squared plus 12 pi squared. That's it. So keep practicing these kinds of questions, as you will have to know this for your exam, how to do these tricks and how to use these tables in order to build more complicated Laplace transforms. What else is there? So yeah, that's what we derived from the previous slide. Now, okay, so we want to find the Laplace transform of Vns of t. So Vn, the Laplace transform of Vn is just equal to 3 1 over s, because remember that the Laplace transform of u of t is 1 over s. So that one's very simple. So we're going to basically have here that the Laplace transform of 3 u of t, which is Vn, equals 3 over s, is equal to 1 over 10, the Laplace transform of d dt of I else of t, plus the Laplace transform of I else of t. So that's just 1 over 10 s f of s minus, sorry, I else of s minus I else of 0, which they gave us that is equal to 0, plus I else of s. And so we have here, we multiply both sides by 10, so we're going to have 30 over s equals s plus 10 I else of s, and that's going to give us that I else of s equals 30 s plus 10, So at this point we're done, but I'm going to do one additional step where I'm going to add 3s to this and subtract 3s, so that I end up with that this is actually equal to 3 over s minus 3 over s plus 10. Then I can take the inverse Laplace, and I'm going to get that ILs of t is equal to 3 minus e, or sorry, oh god, okay, let me just clean this up a little bit. 3u of t minus 3e to the negative 3t, or 10t, sorry, u of t. So you can already see how we can solve differential equations using our Laplace transform. In next class, we're actually going to go over how to go from an expression that looks like this to an expression that looks like this in our inverse Laplace lecture. So that's kind of what's coming forward. So, okay. So this is what I just did in the previous slide. So let's move on. We have 18 more slides, but I think okay, so we already went over this. So let's just keep going.